Today I want to show you how to use Ezra when you already have collected data. EZRA, or as I call it Ezra, stands for Easy Radio Astronomy. This is simply my latest set of software programs to collect and analyze 1420 megahertz galactic hydrogen data. I hope others will find it useful. It is free and runs on Windows and Linux. This shows a hardware antenna in the top left, which sends radio signals to the hardware receiver, which is controlled by some software choice from the second row. You have many choices. Each one creates data files with a different data format. Ezra includes the EasyCall program on the left. It needs no data translation to use Ezra. A popular data collecting program is using SDR Sharp with the IF Average plugin. Ezra already includes a data translation for that. But today I will talk about three other data translation programs for Desperia, SpectraCyber, and MIT Haystack SRT. So all of these data sets contain similar data. What they need is a similar data format, a simple data format. What would be in that simple data format? Ezra suggests a telescope name, the telescope location on Earth, the latitude, longitude, and altitude above mean sea level, and at least one telescope pointing direction. The simplest is azimuth, an elevation above the horizon. And then the data. Each sample should include the starting date and time, the spectrum values, and maybe a flag telling what kind of data this is. I call that an Ezra.txt data file. Those spectrum values are simply the sample's power values for each of the frequency channels. Here it would be the values of these 256 red dots. The first example is Desperia, which we heard about yesterday. Desperia stands for Digital Signal Processing in Radio Astronomy, which is a teaching program from the West Virginia University. It runs on Linux, and they say perhaps on Windows. As they suggested, I ran it on Linux Ubuntu 20. Their instructions led me to install GNU Radio, and from a particular directory I loaded their program, which ends in .grc. I ran the graphical GNU Radio. They said to change two variables in the top right. I changed the long integration time from 10 seconds to 30 seconds. Next time I will try 200 seconds to reduce the number of files. I changed the variable over here to spell the directory where I wanted to save the data files. Then I clicked the little black arrow up on the top, little black triangle on the top, to run the program, and got this graphical interface. With one amplifier, my signal was weak. So I changed this Ymax setting over here from 200 to 1 so that I could see this familiar blue frequency spectrum curve updating. I entered the antenna's proper azimuth and elevation. And here I entered my ham radio call for an antenna name. Then I clicked this button to choose my long integration time of 30 seconds. And I clicked here to choose the full frequency spectrum curve, which includes the ends, which can optionally be clipped off. And then I clicked here to start writing to file. And it began recording. Oh boy, it sure did. It wrote over 2,000 files per day. Each file name included the date, time, telescope name, azimuth, and elevation, and ended with .csv, like a spreadsheet file. Each of the over 4,000 file lines started with a frequency value and ended with a power value. I have run Despera for weeks. I converted a day's worth of data files like this. Here, using the Windows command spelling, I emptied the temporary data directory. Then I ran the conversion program. Starts with py for Python. Then reaching into the Ezra directory to get the easy call, COL for collect, and Despera.py program, followed by the missing information, including latitude, longitude, and altitude above mean sea level. There was Despera records in PC local time, so there is also a time zone change. And I organized the Despera files in subdirectories by their UTC day, here for July 18. That created one .text file in the data directory, and I analyzed it with this second line. Here I ran the EasyCon, CON for condense program, followed by that data directory, followed by this long keyword, which I will explain on the next slide. Note how these two words represent 61% and 68%. Those commands create one file for one UTC day. After automating commands like this for each day, after processing, here are all the antenna samples for that one day, from 0 to 24 hours. Each sample of values is one vertical line. I chose to ignore lots of frequencies above and below the hydrogen. Consider the spectrum frequencies from the bottom here as 0%, down on the bottom, spanning up to here as 100%. The earlier command said to keep only those frequencies from 61% here to 68% up here, and ignore the rest. That removed unneeded and troublesome RFI data. On this day-long data, I see a bright patch over here and over here. After automating commands like this for each day, the Easy Sky program can plot that data on the radio sky. I see power bumps for the galactic plane over here on the left, but the right side is not so clear. The hot summer temperatures here in Colorado have wild daily temperature changes, which affected the system gain. Here is a plot of all the average antenna power values against the UTC day, and we can see that daily variation. My UTC day starts at 6 p.m. local time, and the night temperature cools, the amplifier works better, the gain increases, and the data values increase. Then the dawn arrives about 6 in the morning, and the sun heats the day. The gain decreases, and the data values decrease also. And then the varying winds and clouds cause confusion. It would be nice to capture this temperature variance curve and remove it from the data. That is what EasyCal's frequent reference samples try to do. But this data collection with Despera does not record reference samples. The second example is with SpectraCyber. It has a program that runs on Windows. The SpectraCyber is a hardware receiver box. It has a coax cable antenna connector on the back. It talks to a Windows PC program. It was a long time standard, but then COVID hit, and I think it is no longer for sale. I expect there are still many available on the resale market. The PC program has a graphics screen like this, showing the frequency spectrum power, which can be recorded to a data file. Our Rich Russell provided this data. Rich organized the data files into directories by declination. In the dec +20 directory was this file. Its file name ends in a number, maybe counting all the way up to 999. The file begins with a one-line header with the date, time, and some Doppler frequency information, followed by the sampled data values. I converted one declination of data files like this. Just like last time, I emptied the temporary data directory. I ran the conversion program, again reaching into Ezra to gather the program called EasyCall and SC for SpectraCyber.py, followed by the missing information. Here's the telescope name, the latitude, the longitude, the altitude above mean sea level, and then there was a time zone correction, and entering the azimuth as 180 and the elevation over here, and finally the directory that we're pulling the data from, the dec +20 directory. I calculated that elevation value from the declination and the latitude. That created one Ezra.txt file in that data directory. I analyzed it with the next simple command. These commands create one file for one declination. After automating commands like that for each declination, the EasySky program can plot that data on the radio sky. I see power bumps over here on the galactic plane. EasySky can interpolate to fill in the spaces between data points. Here, the brighter yellow shows the greatest power. And just for fun, EasySky can plot that data in the way Grote-Reber did, way back in 1944. With the galactic center in the middle, EasyGal can start to plot the galactic arms. In the upper left, I can see the start of a more distant arm. This data was collected mostly 1 day per declination. These plots should improve with more data. The final example is with the MIT Haystack SRT program. SRT stands for Small Radio Telescope and is a teaching program from MIT's Haystack Radar Lab. I used the old C language program that runs on Linux. A new version apparently runs on Windows. The old SRT program's graphic screen presents a lot of information. The bottom half represents the antenna's whole currently visible sky. The azimuth increases along the bottom to the right, with 0 at the left for north, 90 for east, 180 for south, and so on. The elevation increases from the bottom 0 degrees for the horizon, all the way up to the top 90 degrees for directly overhead zenith. We can see the arch of the Milky Way on the left. The SRT program can control 2 tracking motors on a dish antenna. The colorful bullseye in the top left is a recent 25-point automated raster of the sun. To the right of that bullseye are recent traces of average power, with time increasing to the right. The bottom spectrum is the latest integrated frequency data. And the text to the right says that integration time is 44 seconds, along with all kinds of other calculations. SRT can be programmed to do complicated automated data collecting jobs over many hours. I've run SRT for months. Here is an SRT.rad data file. The file name includes the year, the day number of the year, and the UTC hour the file began. SRT will start a new data file upon the start of a new UTC day. My modified SRT records 5 lines per sample. The first line has the date and the time and the azimuth and the elevation. The second line lists the lowest frequency and the highest frequency and how many frequencies are represented. 256. The fourth line lists those 256 frequency spectrum values. And the fifth line actually records the use of a USB relay for LNA control. I converted one SRT data file like this. Again, like last time, I emptied the temporary data directory. I ran the conversion program, py for Python, reaching into the Ezra directory for the easy call, and now hay for haystack.py program, and then reaching over to get the .rad file created by SRT. That created one Ezra.txt file in the data directory. I analyzed it with this simple command down here below. Those commands create one file for one SRT data file, commonly one whole UTC day. After automating commands like this for each SRT data file, the Easy Sky program can plot that data on the radio sky. I see power bumps over here along the galactic plane. Easy Sky can plot that data as wide bands with brighter yellow showing the greatest power. Easy Sky can plot that interpolated data on galactic coordinates. See the brighter colors showing more hydrogen along the horizontal galactic plane. The green area of the sky is the sky the antenna location cannot see. The Earth is in the way. And the yellow area is the sky without data. Now using the dish antenna that has motors, galactic plane velocity spectra can be collected for each galactic longitude degree. This is 0 through 89. Stacking those spectra horizontally, like books piled on a table, starts to show patterns. Stacking those spectra vertically, like books on a library shelf, enhances these patterns. Each spectra vertically. With the galactic center as a green dot, I labeled the galactic arms, and collecting data for just the galactic longitude of plus 110, marked by that yellow line. The EasyGlon program can plot the cross-section. Here the arms appear as red blobs in cross-section. The arms are above the horizontal white galactic plane. The galaxy is warped, shaped like a potato chip. This is what Felicia Lynn presented at the Western Conference in Dallas in April. So maybe we can convert your existing collected data. Please give Ezra a try and tell me of your successes. Questions?
Yeah. We have time for maybe one question, and then everything else should go on to chat. We have a hard schedule we have to keep here at Jansky today.
Very
So
good. And at that
any one
website,
question for Ted?
and at that website is my email address.
Good.
Well, thank you very much.